Hello, everyone. Welcome, and everyone online. It's good to see everyone here. I'm not coming from too far away. I'm basically a member of GERAD and GERAD, and I should say coming from just across the street. So today, the presentation is about a contextual framework for learning routing experiences in last mile delivery. So when we order something online, it takes a few days for the shipment, for the preparation. It's going to be shipped to the nearest airport, probably, if it is being shipped from across the country or from elsewhere. And it's going to arrive at the airport. And then the final stage is to receive it at your home from the airport or from a close by facility. So this last step is called the last mile in the delivery process. And it's putting a huge pressure on the delivery companies simply because it's the most costly component of the whole transportation system. According to some research, it accounts to roughly 41% of the total cost, increasing sometimes up to 50%. So that's a huge cost component. And the question is, how can we make these deliveries better and more efficient? So within this context, my research is about the design and management of large-scale networks. And by design, what I mean is the strategic design of such networks, such systems, and the management is more of an operational context where on a daily basis how you do things. And for today, I'm going to be talking about smart last mile delivery systems. So I'll briefly talk about what we have been doing very recently with my collaborators and students, and then we will get started with the algorithm part that is basically related to today's talk. So Zin is among the audience now. She's our PhD student with Eric, and what we are doing in the business model part is basically the strategic aspect of the last mile delivery. For example, in the first one, I'm just going to give you an overview of these papers that Zin and some other students that have been working on. The first one is about using the neighborhood structure in the last mile delivery. So how can I make the deliveries more efficient rather than delivering to each and every one of you? The people in here, I'll just consolidate and deliver to only a few people here so that they're going to serve as my point of contact, like my forward operating base. They will be delivering the parcels for me. That's the topic of the crowd keeping in last mile delivery, where we use the crowd. They're very similar to an Uber structure. There's a platform and they get a compensation for the work they do in return. The second one is about opportunity sales in attended home delivery. So we do these deliveries every day. And why not I just push some notifications to your cell phone so that I can, make a few more sales while I'm doing the operations. So thanks to these smartphone technologies, that is now a reality. And this is the result of a collaboration with some colleagues from Turkey and Professor Gilbert Labor. The last one is about the ultra-fast delivery. You must have heard of this option very recently emerging in the industry, which is the delivery within 15 minutes. That's incredibly fast. And the companies have been popping up similar to the charging station issues back in 2010-ish. And they all went bankrupt. And these ultra-fast deliveries are now giving up on the idea of 15-minute delivery, or they are struggling to make profits. And that's something we have been investigating again with Zin here. On the algorithmic part, there are a few things that also can be done. And today I'm going to be talking about a joint work with Norina, our master's degree student. She's working on learning this experience of the drivers, and that's going to be the topic of today's talk. And Taha is a recent PhD student who's starting very soon, and Aladdin is also working on a similar project in collaboration with Intelcom. I don't know if you have received any packages from Intelcom yet, but in here in Montreal, they are the main distributor of Amazon. So if you order something Amazon, it's highly likely that you're either going to receive it directly from Amazon or from Intel. So we will be focusing on the contextual framework development for learning routing experiences for today. So this is the agenda. The first thing I'm going to try to clarify is what is a contextual framework. And then there was a recent competition organized in 2021. I've been talking since then about this. So sorry if this is going to be a repetition for you. But so I'll give you an overview of what was done, what was that competition about, and all the details. And some of the algorithmic developments that we used for learning the driver's experiences on that front, and some results. So in 2021, I recently presented this at one of the GERAD JOPT conferences, and that was the descriptive part. Now today, what's going to be new is the predictive analytics part. So what is a contextual framework? We start with that. If you ask to Google, that's observing people or users, in our case, it's the drivers, interacting and engaging with a design in their contextual environment. So we are talking about that design here, and I'm going to emphasize that in a moment. The next best thing you can do is probably to ask to ChatGPT, and that's exactly what I did, but without in one single sentence. I just asked the first part, and it just wrote me 5 pages. So I just said, okay, please make it concise. What is it in one single sentence? So in here too, we are talking about a situational context. So the drivers are given some routes, and they are basically interacting with this design, with the optimal routes, that the ones that we think are optimal, and they are interacting with this design and changing it according to their needs. In the scholar world, it's not really too much related to optimization, but very recently, Utsa, who's here, and other colleagues that I see, Eric and Emma here, very recently published a survey on contextual optimization. And I'm going to basically connecting what we are doing with this survey. It's pretty much linked to the prediction and optimization framework they present in this survey. So the issue is, we have been solving the traveling salesman problem for 50 years, 70 years now. We give it to the drivers, and they'll go ahead and change their routes according to whatever measure they take. So we talk about length, duration, and cost, and we believe that it's optimal. But in the end, the route that they execute didn't really turn out to be optimal, and they increased their distances because of some particular needs, what we would then refer to as their tacit knowledge. It could be a parking space problem, it could be some other features that they like, but for whatever reason, they have been changing this. So when we sit down together with them and ask them to articulate their problems, they do not put those in words. But now, thanks to this data, we can better understand what they are doing in real world. So this is basically what we refer to as experience learning. We are going to be learning the experience that they have, but it's not a complete independent experience. We are not giving them a list of customers and expecting them to come up with the route. We are guiding them through our optimization. So we give them the optimal routes. So there's a guidance here. And on top of this, they do this modification. So they are not completely independent in that regard. So this is the situation that I'm referring to here back in the contextual optimization. So the optimization is guiding the drivers. In 2001, Amazon organized a research challenge in which they made available more than 6,000 routes with all the details. How many packages are being delivered? What is the coordinate of this person, and et cetera, et cetera. And I'm going to give you more details on that. It was in 2021, and it lasted almost 4 months. And the data came from 5 different cities in the States. 50% came from Los Angeles, and the others came from Seattle, Chicago, Boston, and Austin. So there are 17 depots from where the routes start, this many routes, and the experts classified them as high, medium, and low quality. Many of them are medium quality in the data set. Some are high and some are low. And the routes are executed in 2018, and this data set is available online for those of you who are interested. And there are some descriptive statistics here. In the data set, there's the route ID from where it starts, the date and the departure time, the vehicle capacity, the stop here we use as customer or the node. So how many stops are going to be served on that route, the observed sequence in which the stops are visited. So we know the actual routes, and we have a route score that I'm going to talk about later in a few slides. We have some stop information about the customers. What is their latitude and longitude? What is the type of this customer, the zone ID type, meaning the difference is only, are we going to deliver something or is it a destination? We have zone ID, which is particularly interesting. The customers are broken down into zones and they don't overlap with the zip codes necessarily. We have packages that are being delivered to these customers and the distance matrix as we know it, but it's time. And we have the package information, including time window and the service time. So they did a great job in terms of providing us a clean data set. And the objective in this competition was the following. You are given such a historical data set, and the objective is to build a model out of this to learn from that historical data set so that when faced with an unknown data, it's going to produce similar routes to those. And I'm going to define what similar is in this context. So there's the model building phase where you can interact with the historical data, learn about extract that information, and I think the time constraint was 3 hours. There's the model apply phase where you generate the actual routes for an unknown new data, and then it is being scored, evaluated, and ranked. So this evaluation is tricky simply because when you simply shift the order of the customers by one, does it mean that it's completely off? Not necessarily. Here, the first customer is taken from the route one and inserted as the last customer, but this is not significantly different than the first one. And similarly here, the route 3 is doing the same route, but in the reverse. So does it mean that it's totally different? So comparing or evaluating the given two routes, how do we measure how much they are similar or not? Yes, please.
Question on the previous one, it was distance information, but that means that the network can actually change?
No, that's yeah. We have the distance matrix, that's it. So it's not changing in time, but we have the distance matrix. In other words, we know when we go to customer stop I, we know how much time it's going to take to go to stop J.
Yeah, but when you generalize, so you have the evaluation phase, the inference, and that matrix. Oh,
that's a good question. No, because the evaluation is not related to the distance. We are not going to measure we are not going to compare the routes with respect to a measure such as we have in the TSV, such as route, cost, or time. It's more related to how similar this sequence is to another sequence. So it's just the ordering that we are comparing, not the distance. And here is what they came up with. So it's related to a sequence deviation, which is just comparing consecutive items in that route. So if you consecutively, if there's a chain that you could identify correctly, that will increase your route score. And for the routes, the perfect score is 0. So if you match it, you get a 0. If you completely mess up, it's somewhere between 0.8 and 1.2, and it's them who assigns this value. So if you mess up in the route or randomly visit all the customers, you're gonna receive something close to 0.8, and the winners of the competition achieved right here 0.03, 0.02. So that's where they lie. And so the first component is about the chains. So if the chains are correct, then you'll probably get better and better scores, meaning closer to 0. The second component is related to what they have in computer science. So you have a word, my name Okan. So if you want to change this to Nako, so it's probably you'll have to do some insertions and some removals. So these operations they are counting this, and it's called edit distance. So how many iterations is it going to take for them at minimum to transform your route into the correctly executed one? So that's a very nice measure actually to compare two routes, and one aspect captures the sequences, and the other aspect captures the other features such as time and such as time. And the submission score is just the average overall all the routes. The competition was announced, and many people participated. And here is a close look about how they came up with their models. And I borrowed these slides from their award ceremony. So it's not me who prepared this. So you see, it doesn't add up to 100 simply because some people just did both. On the predictive side, people tried choice modeling, machine learning, such as convolutional neural networks and graph neural networks. On the prescriptive side, there's constructive heuristics, and we are solving this problem as a TSP. Our preliminary approach for this, me and a colleague of mine, Rashid Abay, participated in this competition, and we developed a prescriptive method. We are on this side of the world, and solved basically a TSP. And I'm going to show you the basic idea and about how we solved this. Yeah, so there are more than 2,000 participants. 45 teams made it to the finals, and the winners were the first one was by William Cook and another Stefan Held and from Germany, and Carl Sagan, LKH algorithm, you know. LKH, H is here, so you probably know who they are. The second team was from MIT, and we came third. So this is the only moment in my lifetime that I could transform an algorithm into a kitchen. So we got some monetary awards out of this. So if you came fourth, it would be a toaster. So we were quite lucky. We just made it, barely made it, you know. Here are some descriptive statistics. So among 1.5 million packages, many of them are delivered on the first round. Some are attempted, and they are being tried again in the same day. So the same route may try the same point multiple times, up to 6 times, again and again, to make sure that they can deliver. And only 32 were rejected. So many of the routes, even though the delivery attempted number is very low, it's on majority of the routes. 59% of the routes include a reattempt on the route. There were 3 types of vehicles, and the average vehicle load is 75%. It's just some insights about what is going on, some descriptive statistics. So the average number of customers is between 32 and 230. And the time that it takes between the service time changes from 40 seconds to 500 seconds. And they have plenty of customers. You see, it's just 1 minute apart that the customers are apart from each other. They literally deliver many packages in the same neighborhood, but the time that it takes from the depot to the first stop is somewhat much larger. So you're loading the vehicle and going to a neighborhood, delivering them and coming back. That's it. That's what is happening. These descriptive statistics, they're nice. They give many insights, but I don't know if you met data source previously, but all the figures, all the data distributions that you see here have the same mean, standard deviation, and correlation. Nevertheless, they are totally different data sets. So it doesn't tell the whole story. So we went ahead and tried to understand what are beyond the descriptive statistics. It turns out that less than 5% of the routes can actually be impacted by the time windows. So it's not really a major concern. And they actually don't mind that much because there are majority of the time they are violated. So the time window, so remember, we are trying to imitate them. We are not trying to respect the time windows. So, and they are not respecting either. So that's something we keep in mind. The travel time still constitutes one of the most important features, which tells us that, okay, the classical TSP should perform well. And in the actual routes, the first and the last stop are not necessarily the ones closer to depot. They can start somewhere else. And then the zone ID is one of the key features for about how they construct their routes. And I'm gonna elaborate on that in a second. So this is a typical route where they spend 30% of the time back and forth and 70% delivering goods in one neighborhood. And this is the first and the last stop on the route classified with respect to how far it is from the depot. Sometimes it's very close, sometimes it's very far away. It makes sense to start either there or there, but there's no clear approach as to how they select this, the first node. So we kept this in mind when building the routes. And this is a typical route. As you see, there are some crosses here that you wouldn't expect to have in a typical VRP, TSP. This vehicle, why is it not visiting this client on the way, but it's just doing a route, visiting a bunch of other customers and coming back. So the idea, the result of the descriptive statistics led us to observe that they are basically following the zone IDs. When these zone IDs are very nicely done, and which is a different research topic probably, but they are nicely designed so that when you enter into this zone, it doesn't make sense to leave. So if you get into the University of Montréal, you wouldn't want to go to Côte-des-Neiges and deliver and come back and forth. It doesn't make sense. There's a road there called the road Côte-des-Neiges. It's hard to cross that road. So they classify these customers into chunks, and they usually follow closely these neighborhood definitions. So observing that, yes. Yes.
Just another clarification. Sure. So in the beginning, you said that you had labels on the route that were like high quality, medium quality, and low quality.
That's right.
So this descriptive statistics, are they on all of the routes independently of their label, or like how are you using the labels?
That's a wonderful question. I didn't start talking about it yet. These are all on the whole data set. Plus, that's a wonderful question, actually. Should we concentrate only on the high routes, or is there anything to learn from the medium and low quality routes? And that's something I'm gonna elaborate later down the talk. Oh, about the zone IDs. So in the descriptive statistics, so this is the zone ID, A, B, 2B. And when you receive a package from Amazon, check the label on it. You're gonna see something like this. And it basically, they divide it, and not surprisingly, A2, 2B is just the neighboring zone, and so on and so forth. So what we did in the descriptive statistics is to implement a transformation. In other words, if they share all 4 digits in that zone ID, then we are gonna multiply the distance by 1. If you're changing the zone, but changing only 1 token in that 4 digit, then we are gonna multiply it by 10. If not, we are gonna multiply it by 100. So but in other words, we encourage and discourage the transitions between zones, not really doing a fancy thing. And plus, we release 1 degree of freedom. In other words, we encourage the drivers to take whatever, or the route generation algorithm, to take whatever customer they want to start with. We multiply it by 0. The distance from the depot to any customer is simply 0. They can start wherever they want to start. And then you see it's just a network transformation. So we have the distances are multiplied by some multiplier, and it is fed into a TSP solver. This can be solved using the LKH algorithm, Lin-Kernighan hexagon algorithm. But within the context of this competition, it was not allowed because it's not under the MIT license, but we used another researcher's implementation of a genetic algorithm, which performed equally well. So this is what led to the third place in the competition. So what is the deal here? We have the physical network lying in here, and we have the third dimension, which is the preferences. So the preference network is basically boosting or adding one more dimension to the network, and we are basically doing the routing in this dimension. And this is the distribution of the scores that we have achieved. So it's 0.03. So remember, the closer you get to 0, the better. And majority of them are really nicely generated. There are some poorly generating ones. And this is the result of the descriptive analytics. And this led to a score of an average of 0.0391 on a data set that was not seen. The first place, William Cook's teams achieved 0.0248, and the second team achieved 353. I'm sorry. Today, in the second part of the talk, I'm going to talk about some black box optimization and sort of a supervised learning algorithm that led to quite a bit of improvements, up to 25% on a testing data set. And on the training, we were able to achieve quite significantly the values. So this is going to be the second part of the talk, which is the experience learning by predictive analytics. Yes, please.
You said in the transformed network, you multiply some distances by 10 and others by 100.
Yes.
10 and 100 seems, okay, default values, like, could you get better results by?
Wonderful point. Exactly. That's exactly the same question we posed. And during the competition, there was not really too much time. But what we did was just to test 400 to be precise, 494 different values. There are sometimes would be small perturbation for each 100, for example. I would add some small perturbation for 10, another small perturbation, and randomly generate some so these 5 values that are in here. So it's based on 5 values only. And we randomly generated, perturbed these default settings, and none performed as good as these ones, which is quite interesting in its own. Yes, so this was exactly the same question that we posed. Can we do better? Does there exist any different AB values that could potentially achieve better results? And plus, those are just zone transitions. Can we take into account some other features? And yeah, that's going to be the second part of the talk. So in the classical OR approach, we would just read the data, solve it, and it's going to be scored. Oh, by the way, when you only take the distances, it still achieves a very good score of 0.07. And I'm going to come back to this at the end of this talk, today's talk. In the descriptive analytics part, we basically pre-process the data, learn some features that an algorithm couldn't maybe learn, but the data was structured. So we were able to transform the graph and solve it, and it scored well. But now, in the last part, which resembles the one in the survey that I showed you in the beginning, can we somewhat learn the transformation, provide a closed loop here. The scoring is going to provide the feedback to the transformation and modify it. And can we do better, basically?
Sorry, the scoring is calculated in all of them according to whatever is calculated, optimized, and whatever executed is.
Exactly. Whatever the algorithm is outputting versus whatever is happening on the actual route. Any questions so far?
About the scoring, I have a question in my mind. You showed that interesting algorithm to calculate the error or the score. My question is why you don't simply consider the total distance, total travel time? If you are comparing 2 routes, maybe simply there is a reason. I was wondering what was that reason.
That's a wonderful question. That's a fundamental question that I'm going to be questioning towards the end of today's talk. But indeed, so the idea is not just to measure the time simply because you don't know the real time in advance. It's just whatever is provided in the data set, the time or distance matrix is just a proxy probably, but it's not going to be truly the real transportation time that will happen. It's just the average over their historical data set probably. That's one reason. So there's no clear measure on how they want the routes to be. They just optimize it and give it to the driver, and they just want to match whatever. That tested knowledge is basically expressed as a function of the sequence of the orders. That's why they have this, which is very costly, by the way. It takes huge amount of time to evaluate two routes. Given two routes, it takes too much time to evaluate and provide a score. So given an instance, we transform this instance and we have a route generator, which is LKH in our case now. It can generate directly on I or by this transformation I, and then we score it. That's basically, we just came up with one transformation among a family of transformations. And the scoring is quite costly. It takes close to 0.2 seconds to evaluate and compare two routes, which is quite costly. And then we average it over all instances, and this will represent your score. Then the real problem that lies under this is minimizing it over the family of transformations. So that's what I'm going to be talking about today. And now, can we basically make this transformation a better learn a different transformation? So this I is a distance matrix, C by C, where C is the number of customers. And the transformation is basically a zone by zone matrix that lies in here. This is customer to zone and zone to customer matchings. And we basically learn this information from the descriptive analytics. You could have represented better. You could have represented probably the package sizes. But our understanding from the descriptive analytics was that zone was important. And even with the zone, we will observe that it's very difficult to learn this information. And if you add more information into this, your data set is getting smaller because the instance size is not really as large. And it becomes, you basically cannot learn. So there's a nice balance between what you want to learn and what you can. So in this transformation, I'm not talking about a family of all transformations that you can potentially apply. I'm talking about some, we are only considering the zone transformations within the context of today's talk. And this is the point that I made previously. We tested various different numbers for those A and B values, but none of them provided better results than 0, 1, 1, 10, and 100.
So here your objective is to to tweak the transformations, or is it to tweak these numbers? Because you are saying the number doesn't matter.
That's a good point. I'm not really saying that numbers doesn't matter, but I'm probably saying that they were nicely selected, maybe.
Okay.
So in here, the solution is no longer a route in this master problem, but it's this matrix. So we are trying to come up with this matrix, and this basically releases us from the AB. So we are not going to learn B 100 versus 99. It can be per zone pair. So from this zone to that zone, what is the transition? So we will decompose this information into this matrix now. Is that clear? Wonderful. So in this major problem, the solution is the penalty matrix. So why we call it a penalty? Because you could see this as an encouragement or discouragement factor. You are basically trying to learn the sequence of the sequence of customers, and what we did is just to encourage or discourage. In other words, we are providing a penalty for taking that transition. That's why we call it the penalty matrix, and it is the solution that we will refer to here. So we have a penalty matrix, and what we do in the classical optimization would be, this would be your solution, variable X would be associated with it, and we generate some routes, and we score them, and we generate one single score, And then we modify the solution and keep this. For example, if you were developing a heuristic, a trajectory-based heuristic, this is exactly what we do. We have a solution, we evaluate its objective function, and then modify the solution with respect to some rule, with respect to some neighborhood definition, and we will just carry on. In here, there are a few things that I would like to focus. One, the scoring function is complex, and you don't have access to the derivatives, and you don't have access to Hessian matrix. So there's nothing available about the scoring function. It's just a black box, which raises the question of derivative-free optimization techniques or the black box optimization techniques. So that's what we tried. In our preliminary analysis, and I don't know if Norina is here, who took the initiative to test many of these, and I thank her for this. So we test several different derivative-free optimization techniques, including mesh adaptive grid search, Nelder-Med simplex algorithm, and others. In this world of black box optimization, 50 to 100 variables is too many. So, for example, take the example of a heuristic. You have some hyperparameters. Learning those hyperparameters even can be tricky. So it takes incredible amount of time because we don't have any access to the derivative information or the Hessian. It makes life much harder, and learning these values, best performing values, is tricky. And in our case, the smallest station has 617 zones, and the largest has close to 5,000, meaning that we have a matrix of this, 600 by 600. So what we like to learn is changes between 300,000 to 23 million. So that's what we are trying to learn, which is not very practical. Many of the algorithms would just run out of memory, and they would simply not improve if ever it can run. So these are some numbers. These are the depots. And I recently noticed, I didn't notice this for 2 years, but the last 2 letters are the city names. So this comes from Seattle, LA, Chicago, Boston, and Austin. And these are the number of zones in those depots. And these are the numbers of medium quality routes, high quality routes. And towards the end of the competition, the organizers didn't want to have some customers repeating on the routes. That's why they have defined a cleaner version, which includes only 1,100 routes, among others. Clearly, if you decompose this and learn per depot, it makes sense. It's because they are in separate, these zones don't overlap per station. So decomposing and learning per depot makes sense. That's what is being done here. So this is the distribution of the routes, route scores. As you see, some of them are performing pretty poorly, whereas some others are performing much better than others. And this is the result of our descriptive analytics or network transformation idea. So now I'm going to talk about 2 other things. Score-guided coordinate search. So it's a coordinate search, very similar to a heuristic, but we are going to be guiding it using the score, but by decomposing the score as well. And this is inspired by black box optimization. And the second one is label-guided encouragement rules, which is inspired by supervised learning. I cannot say that it's a supervised learning algorithm, and the results are going to be, the reason is going to be clearer in a moment. But what is a score here? Is score a value? Yes, that's what they provide to us. But is it a matrix? So if I sum up all I'm just going to be looking at the routes, and for example, for route 1, they execute this transition, and this transition. So I'm going to be adding the route score to these cells. So in other words, I'm going to decompose the score into a matrix, which will tell me how well this transition performs. If this transition appears in the routes that perform well, then you would see a better value here. If not, it will be a high value. So we basically use this decomposition idea, and this is the sum of the scores. This is how many times they appear in the routes that we are going to be evaluating, which leads to a score matrix. So this tells us the average performance of a zone transition. Okay. So we have a penalty matrix, which is my solution, and we have the objective function of this is the score matrix, which happens to match. This is zone by zone, and this is zone by zone. So from the penalty to scoring matrix, it's pretty straightforward. But what about the other way around? Given a scoring matrix, how would I go ahead and modify the penalty matrix for the second on this trajectory of solutions? So I can start with the initial solution, 10, 100, and 1, and I'm going to score it, and then I'm going to modify the penalty matrix accordingly to be able to generate the next solution, next penalty matrix in my solution process. So we don't have the access to Hessian or the gradient, but can be somewhat learned given two solutions and their score matrices, the direction in which they progress. So this solution, for example, this zone was performing poorly and it's getting better. This is performing poorly now. So the green ones are poor and the blue ones are better. So can we follow these directions to generate a new score matrix? And how should I transform this to the penalty matrix? So we tested this idea of using the different solutions to understand how the solutions change over from one transition to the other one. It proved to be very costly, simply because you need to evaluate two solutions and generating. Remember, to generate this penalty matrix, so we have a penalty matrix, we feed it, we ask LKH, hey, can you generate the routes? It generates the routes, so it takes time, quite a bit of time actually, and then we ask to the scoring matrix to evaluate, scoring function to evaluate, and it does, so we generate this. So when we tried doing this, the interdependencies between zones led to too many problems and we couldn't improve. What do I mean by that? So you might want to change one solution, but only one solution. If you change multiple solutions at a time, then this doesn't have a objective function coefficient directly. We give it again to a black box, which is a route generating algorithm, and it outputs us the result, the solution. In other words, the impact cannot directly be measured, and modifying multiple zones at a time proved to be very costly. So the score guided coordinate search I'm going to briefly describe here works as follows. We have a penalty matrix. So in the penalty matrix, we will look at the score matrix, which is right next to it, and choose epsilon% worst performing transitions. Why? Because the score matrix tells me how good this transition performs. And if it performs poorly, I'm going to just assign a high value to it. In other words, I will change only this cell, which is the coordinate search, literally in black box optimization world. We change only one element of this matrix, and then we take a step size of 10, 50, or 1,000, or 100. If it works, then it works. We take that solution and proceed. So we eliminated the transition at one step and improved the solution without creating too many complexities. If it doesn't work, then we take a huge step of 1,000 just to see if it is the zone itself that's creating the problem. So we basically forbid that zone, not just discourage, but forbid that zone, and see if we can achieve anything to go back and forth between these two by changing the step size. If it doesn't work, then we select the second worst performing zone transition. If it doesn't work, we do this as many as gamma times. And gamma is tested some numbers, as you see here, 3, 5, and 10. And if it performs well, then we take it. And the best performing hyperparameters are these. So what are we doing basically? We have a score matrix, we have a penalty matrix. We look at the score matrix. If you are performing well, we will assign a very high value in the penalty matrix and solve it, find the next solution for the penalty matrix, and keep doing this using the rules that we described here. Vaguely speaking, well, this is similar to coordinate search, but we have found a way to guide the search using the scores by decomposing the score into a matrix rather than a single value. All the discussion is nice. It improved the training score somewhat, up to 10%, but the out of training, the testing sample was not improving, but it was giving us the same or worse solutions. So in the end, we finally have an algorithm that works contrary to all the previous ones, but failed to produce good results. And this was the first algorithm that actually worked among all the others. So this led us to the second idea that I'm going to be talking about now. So this is what we are doing. So we have a penalty matrix, we have a score matrix. Hand in hand, they produce new penalty matrix. We score it, and hand in hand, so on and so forth. So we try to follow a trajectory and find a local optimum, basically, in search. And the initial solution would probably be the one that we started off with. By the way, all the learning is done on the, in here, all the learning is done on the high routes, and the split is 80% to 20% between the training and testing. And in here, what is it we are trying to reach? We are basically trying to reach or guide, thanks to the scoring matrix, to the executed routes. So why don't we simply go ahead and look at the executed routes and see how they perform in the transition matrix? So what we did is, the data here is used, for example, the distance matrix is used here, and the actual data is used here for scoring. We are actually not using the actual routes to learn anything. So what we did on top of all these previous ideas is to learn the scores and incorporate that information into the transition matrix. So this should have been much more obvious upfront, but it wasn't clear to us. Thanks to this scoring matrix, score decomposition, and all the efforts spent on in that dimension, it led us to understand that, hey, you can do it in one single shot. You can basically score the, generate the score matrix of the executed routes, the real routes, and then learn it and generate the corresponding penalty matrix and just solve it in one single shot. That's why it is inspired by the supervised learning algorithm, but it's not really a supervised learning algorithm. It's just inspired by the data set, let's say. And it ended up performing much better in the testing data set. So here is the test and training split. 10% is for training and 90% is for testing. Contrary to this, at the bottom, 90% is learning and 10% is testing. And as you see, when we just learn it directly from the data, the score is improved significantly on the testing, and maybe not surprisingly, it performs equally well in the test, in the testing data set as well. As you see, when we have a large data set, the learning is, we are basically learning and improving with respect to the baseline algorithm that we compare. In other words, with respect to 1, 10, and 100, we improve the scores close to 70% on the training data set and close to 25% in the testing data set. This is for the clean routes. And interestingly enough, the learning, this idea also works on the high routes as well as the medium routes. So regardless of how poor or good or bad they performed, the learning, this idea of just looking at the data set and generating routes out of it works well, equally well in the medium and high routes as well. And you see, when this training and testing split is increasing, in other words, when we have more data to learn, the testing performance is getting better, as you see. The testing performance is getting better. So I'm going to talk about the good things about what I have just described, the bad things and some ugly things that I learned in this 2-year framework. So the good thing is, whatever is being generated here is effective. It turns out that it imitates the drivers very nicely and can execute can generate routes that are closer to the executed routes. They are interpretable. You don't need a crazy machine learning algorithm that tells me something I don't know what it is. It is just generating a zone transition and tells me how likely it is to appear in the solution. That's it. So you don't have intricate relationships between different features, but it is possible also, in other words, it is flexible to incorporate some additional information if you have the computational power to handle it. If you want to decompose this and include the weather information, the site information that's available for that day, yes, you can learn that the historical data on that day and generate routes similar to those. So from that aspect, it is flexible. The bad is, so we have been generating these routes for long years and giving them calling them up as optimal. And these people, I mean, at Amazon wanted us to imitate the drivers. So who is really the right here? Are we supposed to be guiding the drivers to choose better routes, or should they be guiding us to learn what should be executed on the terrain? So that's some of the things that is being learned here might be some incorrect practices of the drivers as well. There's the coffee shop that the guy wants to visit on every route, then we learn this. So is it really a good idea to learn directly out of the data set, or is there a way to discriminate these two ideas? I don't know. The ugly part is the data set is released by Amazon, which was quite nice, and they didn't give any information up front as to how they constructed the routes. But it turns out that the routes are quite structured. So these Amazon drivers seems to be following strictly the rules of zone transitions. So it gave us quite a bit of information. So the tested information that they claimed existed in the data set really didn't exist that much. So they were doing the zone, finishing up the zone, and then transitioning to another zone. And they probably had a sequence of zones in their mind or on a piece of paper that they had. And we just tried to learn that information. So this doesn't really mean that we are learning the tested information. That's the ugly part with this data set. Probably we are hoping to overcome this challenge with together with Intelcom, simply because we will be able to have more access to more data. And the causality is another problem here. So we simply say how close you are to that route is better, but if you are changing something that is significantly changing their operation, so if you want them to use a road segment that is blocked, so it may lead to different questions. So that's the part that which is the ugly part here. But thanks to this encouragement and discouragement idea of the interpretation, you can always, for example, if you don't want the transition to appear in your solutions, you simply set it a high value. Very nice. So that's the good, the bad, and the ugly. So does this offer a general preference learning? Maybe if you are doing a nurse scheduling, can we do the same? So can we learn the objective function coefficients with respect to how we schedule the nurses on every day? And if these two people are close friends and they always want to be scheduled together, can we observe this in the data and generate similar things? So rather than asking people, are you close friends? Giving them a matrix of people and scoring them as to how close they are with that person, we can learn that from the data and maybe incorporate that. That opens a new dimension. And the generalization to BRP is not straightforward. We always talk about the scoring function, but that scoring function is really an ugly function. And it's something that Amazon dictated during dictated is not the right word here, but they had this in the competition. Could we simply look at the arc, the variables and measure the differences between the arcs? As simple as that. Which is an interesting idea used by recently in the context of an inverse optimization. So on the same data set, they used inverse optimization to learn the preferences and use this measure, which is very easier to evaluate. And they have achieved equal results, but not as good as ours. And is scoring essential? That's that's the question. And the experience, I basically talked about it. What we try to learn here is long-term memory, but it can also work on a day-to-day basis, learning the better, etc., etc. So thank you very much for your patience and for listening to this.